4.52, Drawing Molecules. I want to start by looking at the reference sheets. Of course, we know that this one shows us the valence electrons, and we're going to be focusing on just the nonmetals that form covalent bonds. So this section that I've circled, and also hydrogen is going to show up a lot. It's a nonmetal and it forms covalent bonds. If we look at our bond chart, this is great for visual learners because it helps you to see how that atom might look in a molecule. But I want to make sure you know that when you look at this column here with carbon, carbon would look like this in molecules. And there's 4 ways that carbon can get its 4 bonds. It can have 4 single bonds. It can have a single, 2 singles and a double, to add up to 4. It can have the triple and the single to add up to 4, or 2 doubles. So with math, it's like 2 doubles is kind of like 2 plus 2 is 4. And so getting 4 bonds can be done in lots of different ways. Now that's true for carbon, but it's also true for silicon, Si, because Si is right below carbon in that same group. Si has 4 valence electrons, so it also needs 4 bonds. So if you see Si in a molecule, it's going to match what you see here for carbon. Same thing with group 15 with the nitrogen group. That would be how nitrogen might look in a molecule. It can get its 3 bonds in 3 different ways, but that would also be true for P. So if you see P or phosphorus in a molecule, it would also always have one of these patterns that you see here, with either 3 single bonds around it, a single and a double, or just 1 triple. And oxygen in the next group, with its 2 bonds, there's only 2 different ways it can get that, but that would also be the same pattern, the 2 singles here or the double. You'd see that same pattern if you had S or Se in the molecule. Anything from group 16 will make these patterns. So we're just showing oxygen as the example for group 16. And finally, the ones that only need 1 bond include both hydrogen, which only needs 1 bond, and it only has 1 electron, so it is stable like that, and there's no dots around it. But then the halogen group, group 17, and that includes all of these, F, Cl, Br, and I, they all would look like this when they're in a molecule. So it isn't just F that would look like that, but any of the halogens. So when I am drawing these molecules, I want each atom that's in the molecule to look like one of those options. If you're a visual learner, you might want to think about that. How does it look? And otherwise, you can think about it more in terms of the valence electrons and the number of bonds adding up, if you like that better. So I'm going to read through the directions and do these examples. So last week you drew molecules in assignment 3.4 after building them with your models, and now we'll try to draw them without building the models first. So number 1, you're going to determine the number of valence electrons each atom has, and we use the periodic table for that. And then the second one is to find the number of bonds each atom needs to become stable. And since they all want 8 electrons, we take 8 minus the valence electron number. Remember, there is one exception. Hydrogen only needs 1 bond. So let's do those first 2 steps down here on example 1. The valence electrons for carbon, hydrogen, and sulfur, and then the bonds. So if you have your paper, it's maybe easier than moving around on here. But we see carbon, the valence electrons are 4, hydrogen is 1, and sulfur is in the oxygen group, so it has 6. I'm going to write that here. Carbon was 4, hydrogen was 1, and sulfur was 6. Now the number of bonds I can do by subtracting 8 minus the group number. So for carbon, 8 minus 4 means carbon needs 4 bonds. Hydrogen's the exception. It always needs 1 bond. And sulfur 8 minus 6, it needs 2 bonds. So somehow I need to make these atoms all get the bonds that they need together so that they're all stable. So the next step, step 3, use the formula to know how many of each atom there are. The subscript number tells you there are more than one. For example, H2 means 2 H atoms. So in my formula, there is a 2 after the H, so that means 2H. And that little number always goes with the letter that comes before. So in this case, it's 2 H's, not 2 S. So I have 1 carbon, 2 H's, and an S to work with. Now this is kind of important tip here. In the middle, write the symbol of the atom that needs the most bonds, or atoms if there's 2 that need a lot of bonds. So here, carbon needs the most bonds. So I'm going to imagine this space for drawing my molecule. So I'm going to put a C in the middle because I know the one that needs the most bonds has to be in the middle where it can get bonded to many things. Next step, write the symbols of the other atoms around that one and connect them all with a single bond. So I'm going to kind of do these two together. So I have 2 H's and an S, and I'm going to start putting them around this carbon. It doesn't really matter how you put them, just sort of all the way around. When we look at our chart over here, we see carbon often has things coming out to the top and things. It can be trigonal, it can be tetrahedral sometimes. So now I'm going to connect everyone with a single bond. One single between each there. All right, now I'm going to check the bonds. Do they all have what they need? And if not, I'm going to add double or triple bonds. And you also can use the bond chart. So if I'm looking at the bond chart, I see H is got 1 bond here. So I don't really want to add any more bonds to the H, but the carbon, to get 4 bonds, it's going to need some more bonds. It only has 3 things to bond to. It's going to look something like this, with 2 singles and a double. And then sulfur, remember we don't see a sulfur here, but sulfur would be the same as oxygen. So you can see that like oxygen, sulfur can have 2 single bonds, and it could also have a double bond. So since I can't add any double bonds to my hydrogens, I'm going to add that between the sulfur and the carbon. Now let's check that the mathematic way. If I see that H here says it only needs 1 bond, and I already have 1 bond there for that H, I can't add another one there. And I have a bond here for that H, so I can't add a double bond in either of those spots. But because the sulfur needed 2 bonds, and before it only had 1, and the carbon needed 4, and before it only had 3, that means that adding that double bond there works. Now finally, you don't have to show the unshared pairs. We're focusing more just on the bonds, but it is important to know that they are there. So if you want to try it, you can. I would do that probably by looking at these valence electrons, and I see that carbon has 4 valence electrons and they're all in the bond. So it does not have any unshared dots. And hydrogen has 1 and it's in the bond. But the sulfur has 6 valence electrons and only 2 are in the bond. So that means the other 4 to make 6 are dots. So I'm going to put 4 dots, and I like to put them in pairs, so 2 pairs kind of there. Again, using more visual way, when you look at the chart, we see the S, and I guess I kind of covered up the dots, but S would look just like an O, and you see how it does have those 2 unshared pairs or 4 dots around it here and here with the double bond. So it's kind of a puzzle to just make everything happy. Let's try the next one. Going back, We're going to do the valence electrons and the bonds. I remember we just did it, so carbon was 4, hydrogen was 1, and then this is Cl. When you see capital C and it looks kind of like an I, that's Cl, chlorine. So that's one of our halogens. And you see that F here, but Cl would look just like that. So it has one bond. But I also can look up here. I guess we were doing this part, right? So Cl is over here in the halogens, and it has 7 valence electrons. Now for bonds, we do 8 minus the group number, or 8 minus the valence number. So 8 minus 4 means carbon wants 4. Hydrogen's the exception, it only just wants 1 bond, but 8 minus 7 for chlorine means that also wants 1 bond. Now I'm going to look at the subscripts. They all have a 2, so that means I have 2 of everything, and I have to make it work. So everything is stable, and everything's part of the molecule. So I'm on step 4 now. In the middle, write the symbol of the atom or atoms that need the most bonds. So this time I have 2 carbons, they both need 4. So I would put both those carbons kind of together in the middle. They're going to need a lot of bonds. Then it says, write the symbol of the other atoms around that one and connect them all with a single bond. So I would sort of distribute them evenly, maybe like try an H on each side and a Cl on each side, or on each one, kind of thinking of each carbon needing 4 bonds. So then connect with single bonds. So that looks kind of good, right? But now we want to check. This time I'll start with the math way. We know that carbon wants 4 bonds. So I'm going to look at this carbon here, and I'm going to count how many bonds it has. 1, 2, 3. That's not enough. Let's look at the other carbon here, and let's count how many bonds it has. 1, 2, 3. That's not enough. So we know hydrogen can't take another bond, so I cannot put a double bond between a C and an H. We know that Cl only wants 1 bond. Oops, didn't mean to erase that. Just going to highlight that. So the Cl only needs 1 bond, and it already has one touching it. And this Cl does too. So we can't put double bonds there, but since both carbons need another bond, we can put a double bond between the 2 carbons. So this looks pretty good. And now if you want to check the visual way, it's a bigger molecule, so you have to kind of zoom in and look at one part at a time. If I look at this carbon, does it look like one of my options in the bond chart? And when I look, it does look like, again, that 2 singles and a double again. And then the chlorine, the Cl, would look a lot like this F with 1 bond, and the H should just have 1 bond. And let's double check our other carbon. It also has the double bond and 2 singles there. So that looks pretty good. Both the visual way matches the pictures and mathematically. Now let's think about the unshared pairs. You don't have to show them, but again, if we compare our bonds to our valence electrons here, compare the top to the bottom here, when they're the same, like 4 and 4, that means all 4 of the valence electrons of that carbon are in the bonds, because each bond has to have 1 from that carbon. And with the hydrogens, the 1 valence electron it has is in the bond, so there's no dots around those. But the Cl, when I look at, it has 7 valence electron and only 1 is in the bond. That leaves 6 dots around it, 6 unshared electrons. Let's look at the last one, the last example. So I have now Si, N, Br. I want to know the valence electrons. So I'm going to look up here. We see Si is under the carbon, and it's got 4. N has 5. And Br is one of the halogens, and it has 7. So 4, 5, 7. Now to get the number of bonds, I'm going to subtract 8 minus the valence number. So 8 minus 4 is 4. 8 minus 5 is 3. 8 minus 7 is 1. So this Si with the 4 bonds, that's a lot like carbon, isn't it? It's exactly like carbon in how it will bond. The next step, if you don't remember, you can look up here, but we want to put in the middle, where it's circled, number 4, write the symbol of the atom that needs the most bonds. And we have silicon with 4, so I'm going to put that first. But N also needs a lot of bonds, so I'm going to put N, and I'm going to connect those. And now notice we have one more, Br. So think about which one needs the most bonds. So even though they're in this order in the formula, Si, N, Br, I'm going to put the Br over here to make sure that Si gets what it needs. If I start trying to put the Br over here, the Si might not get enough. All right, now I'm going to do it the math way again this time. So we see that everything's connected with a single bond. Now Br already has 1 bond. It can't take any more. But the Si needs 4, and I see it only has 1, 2 around it. And the N needs 3, and it only has 1. So they both need more bonds. So I'm going to start by putting a double bond between the Si and the N. Now, the Si has 3 bonds, but it still needs 1 more to get 4. And the N has 2 bonds, and it needs 1 more to get 3. So that means I need a triple bond here. So let's check the visual method. Si with a triple and a single. Does that match one of our pictures up here? Remember, Si is like carbon. So there is one with a triple and a single here. And then N can also have a triple. And so, yes, that looks like that could be possible. Now, Br over here is going to have 1 bond and 6 dots. So these patterns do seem okay. I kind of think it looks a little messy the way I drew it, so I'm just going to straighten it up a little bit. Doesn't matter that much, but and I can use math also if I want to try to do those unshared pairs. So we know that for Si, all 4 electrons are shared in the bonds, but for N, there's 5 electrons and only 3 are in the bonds. So it's going to have 4, 5. It's going to have 2 that are unshared. And for Br, there's 7 electrons and only 1 is in the bond. So 1, 2, 3, 4, 5, 6 shared because 1 is in the bond. All right. Good luck and come to a Google Meet if you need help.